Hello, this is Mr. Dobson and this is my second video on gravitational fields. This video number 2 is about Newton's law of gravitation. So just a quick review. Video 1 was about the gravitational field strength. So if we look at the formula booklet bits that are relevant. So last time we looked at this, G is equal to F over M. We normally see it as W equals mg, but this is a rearrangement here where W is written as an F. And that tells us about how strong gravity is felt on every kilo of our bodies at sea level. So this is the force per unit mass. So force per unit mass at sea level. Now, we did also mention in the last video that actually this is based on the idea of a big mass and a test mass. And that if we have a large mass, something like a planet, we can call it capital M, and we have a small mass we call little m, we can call this a test mass. We can think about what happens to this as it moves around this big mass. And we do it this way because the idea is that the little mass has negligible mass compared to the big mass, and therefore its gravitational field has a negligible effect on the big mass. Therefore we basically ignore it and the mass becomes nice and easy. So today we're going to look at a much more basic idea. So we'll get rid of our large planet, and what we'll do instead is we'll bring another small mass in. So here's our other small mass. Now, because we've got two small masses, to designate between them, we're going to need to number them. So we're going to call this M1 and this M2. If I can draw a little 2 in there, excellent. Okay, so Newton worked out an equation for us. And the equation is F equals minus capital G M1 M2 all over r squared. Okay, now we need to pick apart what this means. So, first of all, it's saying F. So this is going to measure the force between the particles. Now, we know, or between the masses actually would be better, we know that two masses, if they're in a gravitational field, will sit in that gravitational field, they'll interact with it, and they then allow the field to do work. Basically, the field can then do something. Up to then, the field's just sitting there, kind of mind its own business. Stick a mass in it, the field can now do work. So these two masses can do work on each other. That means there is a force between them, and that is what this is measuring. So the next thing, we've looked at the fact this is a force. We have the masses here. Now, it's quite obvious to us that the masses are going to be very, very important, because we know the size of the mass of this and the size of the mass of this are going to greatly affect the gravitational field around them. If we have a very big mass, very big field, very small mass, very little field. So the mass is obviously very important. Now, the bits that are possibly would come to us but maybe not so immediately obvious, the distance between them is important. So r in this case is the distance between them. So if we was to measure the distance of M2 from M1, okay, that would be our r. It's divided by the distance between them squared, which is quite interesting. That gives us something called an inverse square law, which we'll come back to later. Then we have the G, big G. So if we look over here, big G is the gravitational constant. And the best way to think about that really is how strong the gravity can be, the force of gravity itself, that field, the strength it has. Then you multiply that up by the mass that you put in that field. So this is a measure of how strong that is. And then the little g is much more to do with how we would feel it then as a force. So this is about the strength of gravity itself. That's the best way to describe it, I think, or the simplest way. So G is a measure of the strength of gravity, which we're going to need to know if we're going to want to know how strong the force is. There is this one little extra bit. Now, it's not in the A-level book, but there is technically a minus there. The reason for that, force is a vector, so we must consider whether it's positive or negative. And we've measured R in reference as a distance from M1 to M2. So we've measured R going from M1 to M2. The force, on the other hand, is going to try to attract M2 back to M1, and therefore the force is going to be in opposition, theoretically, to the distance between the two. Now, it's very much the way you look at it. If I was to instead choose, if I swap colours and do it in a different colour, I could quite easily choose to measure the distance this way, call this R prime or something. Then theoretically you could say, oh, but that's the other way now, but then theoretically so would the force. The force we would now be considering in the opposite direction. The force would be pulling M1 to M2 because I've measured from M2, and again it would be negative. So that's where the negative comes in. We don't have to overly concern ourselves with it. You'll just have to remember that sometimes you're going to get things like that because we're dealing with forces, we're dealing with vectors. Now, one thing we do need to think about here, a little tiny adjustment to what I've drawn here. Where I've drawn the radius, I'm not really being as accurate as I could be with that, because as we talked about in the first video, we need to think about things radiating out. That is a terrible straight line, we'll try that again. Things radiating out from the centre. The radius is actually the distance between the centre of masses of the two objects. So I really would be more accurate if I was to draw R in something more like that. So it's the distance between the centre of masses, because the mass can be considered to be acting at the centre of the object. It is worth pointing out that if we were to look at the units of this equation, we would, and if we do a little bit of mucking about with the equation, you could actually work out that we've got newtons, we've got 2 lots of kilograms here, and we've got meters squared, and then what do we find? Newtons, meters squared, kilogram to the -2. You can see that the actual value of G is dimensionally consistent, which is very important. So that's the simple law of the force between two objects, and that is Newton's law of gravitation. Now, it's worth extending this slightly in this short video to consider what that would look like on Earth, because this should theoretically lead through somehow to the last video, because this is looking at the concept of two tiny masses. Last video we looked at a big mass and a little mass. One should lead through to the other. It should be the same for everything. So let's look at that situation. If we were to get some extra room here, where should we do it? Down the bottom here? No, there, so we can still see the equation on the side. We have a large mass. Let's put that up here. Big M. And a little mass, little m. Okay, so that's supposed to be a little m. Let's try that again. It's quite hard to draw a little mass on an iPad screen. Let's try it. There we go. Right. So we can rewrite this equation more specific to this situation. So let's say the force experienced by the little mass, because of the big mass, is equal to minus G m, capital M that is, little m over r squared. Okay, now we know that, going back to the last video, zoom in here, G, little g that is equal to F over m. So if we can turn this equation to, instead of F to F over m, what's left on the other side should equate to little g. So we can do that because we have an m over here. We can simply take it through to there, and then we can do F over little m. So that's the force per unit mass. That's the force experienced on every unit of mass, or every 1 kilogram of mass of our bodies, will be equal to minus big G, big M over R squared. Okay, now we said in the last video that little g is the force experienced per unit mass at sea level on Earth. So we should actually be able to put some numbers in here. First of all, we can put in the value for g, 6.67 times 10 to the minus 11. So let's put that in. So we've got 6.67 times 10 to the 11. Now we've got to times by the mass of the Earth. Well, luckily the formula booklet comes in with that for us. The mass of the Earth is 5.98 times 10 to the 24. So put that there, 5.98 times 10 to the 24. We'll divide that. Now, the distance between the two objects, so we have to think about this, the distance between the two objects. In this case, we have to consider the distance between the centre of the Earth and the centre of the test mass. The centre of the Earth, well, that's easy enough, we kind of know where that is. The centre of the test mass, well, if we're saying at sea level, the centre of the test mass will actually be the radius of the Earth away from the centre. Think about what that means. If I go back up to my big mass here, what we're thinking about is a test mass here that's placed at sea level. So its mass is considered to be exactly on the edge of M. Now, theoretically, therefore, if here is the centre of the Earth, the distance from here to the centre of this mass is actually the radius of the Earth. Okay, and the not that bit. And the radius of the Earth we're given as well. Here it is, 6.37 times 10 to the 6. So we can put that in down here. 6.37 times 10 to the 6, and of course it's r squared, so that's that. Now throw them numbers in your calculator, but with that as a minus, because that should be times 10 to the minus 11. We'll throw the numbers in the calculator and we get 9.829, so roughly 9.83. And the units of that, well, we can see we have newtons here divided by kilograms, so the unit would be newtons per kilogram, which we know to be the units of little g. Technically, obviously, we know at sea level we've got a value of 9.81 that we use, but this is the mean radius and there's a little bit of errors and stuff like that in here. 9.83 is perfectly acceptable. So we can see that Newton's law of gravitation is actually what gives us our value of 9.81, or in this case 9.83 newtons per kilogram at the surface of Earth. So we've got in the last video we got the concepts from what a field is and how a gravitational field might work. We brought in concepts from GCSE of little g and the strength of gravity on every kilogram of mass at the surface of the Earth. Now we've taken it one step further. We've looked at Newton and what Newton actually worked out, his equation here. We looked at how that works between two small masses, but we've also considered it with a large mass of the Earth and a small mass around it, how you could rewrite the equation ever so slightly to accommodate that, a little bit of manipulation, and put the numbers in for Earth specifically, and we find we have little g. Okay, that's the end of this video. Thank you for watching.